If you want a short version of the legend, a seemingly small, almost academic idea about radiator ducts, first written up by British engineer F.W. Meredith, was turned into a practical, surprisingly powerful advantage on the North American P-51 Mustang. Couple that with the Mustang's clean aerodynamics, a monster of an engine, the Packard-built Merlin, and unusually large internal fuel capacity, and you get an airplane that could escort Allied bomber streams deep into Germany and still come back. The result was a fighter that, in real operations, consistently outflew or outlasted its German adversaries. By the late 1930s and early 1940s, aircraft designers faced a brutal trade-off. Engines needed large cooling radiators to keep from boiling over, but every radiator dumped drag into the slipstream. More horsepower demanded more cooling. More cooling meant bigger ducts and more drag, a vicious cycle that cost speed and range. For single-engine fighters, drag and fuel economy were the difference between getting home and not. The P-51's designers were operating inside this constraint, and they decided not to accept it as immutable. Francis W. Meredith, an engineer at Britain's Royal Aircraft Establishment, did something that reads like an engineering parable. In the mid-1930s he analyzed what actually happens to the air that passes through a liquid cooling radiator. Instead of thinking of radiator airflow as pure loss, Meredith realized that the airflow is compressed by ram pressure, heated by the engine coolant, and then expelled through a suitably shaped exit. If the duct and outlet are shaped exactly right, the warmed air can be accelerated rearwards and produce a small amount of thrust, or at the very least cancel much of the radiator's drag. In other words, the radiator could be a tiny jet. That's the Meredith effect. This was not a free energy trick. The thrust comes from using heat that would otherwise be wasted, but in an era when every mph mattered, the payoff could be decisive. Meredith's paper, 1936, was not a fantasy. It was an invitation to think differently about how to route cooling air. North American Aviation's design team, led by Edgar Schmood and others, produced a very clean-looking fighter in 1940. But what made the Mustang special were not only its laminar flow wing and tidy fuselage lines but also how the team handled the engine installation and cooling. The prototype P-51 had carefully thought-out inlet and outlet ducts for the radiator. Early wind tunnel tests and operational refinements produced a fixed inlet with boundary layer bleed and a well-shaped outlet that let the warmed air exit in a manner that either neutralized radiator drag or produced a small forward push at speed. In short, the Meredith effect was deliberately used as an aerodynamic design tool on the P-51. That ducting and radiator arrangement had two big, practical consequences. First, it reduced the drag penalty of a liquid-cooled inline engine installation compared to clumsier cooling layouts. Second, because the duct could be large and slow-flowing, the core could be efficient at cooling without requiring super-high airflow, another drag saver. The net result was an installation that helped the Mustang be faster at the same power setting than many contemporaries. The headline, "Outfly Every German Fighter," needs two clarifications. First, outfly means more than top speed. It includes climb, high-altitude performance, maneuverability at combat speeds, and, critically, endurance range. German fighters like the Bf-109 and Fw-190 were superb short-range interceptors, but they were usually operating from forward bases and had limited endurance when trying to chase deep penetration Allied raids. The P-51 solved the range problem in two ways. By being aerodynamically clean, so it used fuel more efficiently, and by carrying much more internal fuel than most contemporaries. A P-51C, for example, had something on the order of 200+ gallons of internal fuel versus around 80 to 90 gallons in many fighter designs, and it could accept large external drop tanks for still longer missions. That combination let Mustangs escort bombers all the way to and from Germany, denying the Luftwaffe the free shots they had enjoyed earlier in the war. So when people talk about a crazy fuel system, what they often mean is the Mustang's total approach to fuel and cooling: big internal tanks, efficient aerodynamics, and minimal drag from the cooling installation. Together those choices turned the P-51 from a good fighter into a strategic weapon. The Mustang's early versions used the Allison V1710 engine, which worked well at low altitude but lacked the two-stage, two-speed supercharger that gave the Rolls-Royce Merlin exceptional high-altitude performance. The real performance revolution came when the Merlin, built in the US under license by Packard, was fitted to the Mustang. The Merlin's supercharger gave strong power at combat altitudes, and the P-51's clean airframe and efficient Meredith-style radiator installation let the whole package show its teeth. Put bluntly, the Merlin gave the Mustang the horsepower at altitude, the Meredith-style radiator and ducting kept drag low, and the big internal fuel load let Mustangs stay with the bombers. That trio, engine, cooling duct, fuel capacity, is why the Mustang's climb, speed, and endurance outclassed many German fighters in the 1943–45 period. The Germans had excellent fighters, but many of their best machines either couldn't match the combination of speed and range or were constrained by shorter endurance during deep escort fights. A Mustang could chase, disengage, refuel its tactical options, and re-engage in ways the Germans found increasingly costly. Allied strategic bombing depended on fighter escorts. Before the long-range Mustang arrived in force, Allied bomber crews suffered appalling losses beyond the protective umbrella of shorter-ranged fighters. The P-51 changed the calculus. Mustangs could accompany the formations all the way to target and back, keeping German fighters off the bombers, suppressing interception opportunities, and gradually grinding down Luftwaffe strength. Historians argue convincingly that the Mustang's arrival as an effective long-range escort was decisive in giving Allied bombers a survivable campaign over Germany. That's a strategic, not just a tactical, consequence of the engineering choices. It's tempting to credit the whole victory to a single, crazy, engineer, Meredith for the ducting or Schmood for the design, but the truth is collaborative. Meredith provided the conceptual spark for recapturing radiator drag. North Americans' designers, Schmood and colleagues, married that idea to an exceptionally clean airframe and clever ducting. Packard delivered reliable, high-altitude Merlin power, and tactical commanders used the resulting aircraft to change how the air war was fought. The phrase, "one engineer's crazy fuel system," makes a catchy headline, but the miracle was systemic. An idea about heat became a practical drag reduction tool, combined with fuel and engine choices, that transformed performance. Technical papers and pilots' reports both agree on this. Radiator installations are a big aerodynamic tax, particularly at high speed. The P-51's under-fuselage radiator was not hidden for fashion. It was shaped and managed to let the exhaust of warmed air produce useful forward thrust at cruise and high speed, offsetting drag. Pilots noticed the Mustang's ability to maintain high speed without excessive power settings. Engineers saw how the duct's expansion and nozzle shape influenced pressure recovery and exit velocity. The real victory here was converting something that had been purely a cooling necessity into a marginal propulsion element that improved overall efficiency. Popular retellings often overdo the single engine, single engineer angle because it's a neat story. The truth is layered. Meredith's 1936 paper gave a theoretical tool. North American made practical aerodynamic choices. Packard produced Merlins, and pilots and commanders exploited the package. Every great machine is the product of a lot of small, sometimes crazy, innovations stacked together. In the Mustang's case, one of the craziest innovations, treating radiator exhaust as potential thrust, played a surprisingly large role in letting the aircraft fly faster and farther than many expected. If you ask a flight mechanic which single thing made the P-51 dominant, you'll get a dozen answers. The romantic headline, "One engineer's crazy fuel system," is shorthand for a more interesting engineering moral. Small, counterintuitive ideas, when applied intelligently inside a larger system, can be decisive. Meredith's work redefined a problem, cooling drag, as an opportunity, waste heat thrust. The Mustang's designers, engine builders, and crews converted that opportunity into strategic advantage. The result was an airplane that, in the hands of good pilots and supported by smart logistics, helped tip the air war over Europe.